We can now examine what happens to the pressure pattern as the angle of attack changes, starting with low angles. With an alpha of -4 degrees, the drop in pressure is the same above and below the section. There is no differential, and therefore no lift. This is known as the zero lift angle of attack. At 0 degrees alpha, there is a pressure decrease over the upper surface compared with free stream flow, with a smaller decrease on the underside. Even at small angles of attack, between -4 and 0, a positively cambered section will produce lift. The positive pressure at the leading edge is dynamic, or in this context, stagnation pressure. As angle of attack is increased, here to around 4 degrees, the lift force is increased because of the greater acceleration of the upper surface flow in the reduced cross-sectional area of the local stream tube. The low pressure peak moves forward as the angle of attack increases. At 8 degrees, the peak is higher and further forward, and nearly all the lift is from the upper surface. But the increased frontal area means that stagnation pressure is adding to the rearward force. At about 14 degrees, the low pressure peak is well forward, and the high pressure area under the wing is greater, adding to both lift and drag. The contribution to the rearwards force is due to the pressure gradient, which is a change in pressure over distance. The greater the pressure difference, the steeper the gradient. As air tries to flow from high to low pressure, a favourable gradient is one in which the pressure is falling in the direction of the airflow. And an adverse gradient is one in which it is rising in the flow direction, such as between the point of minimum pressure over the aerofoil and the trailing edge. The gradient increases with angle of attack. As the angle of attack reaches about 16 degrees, the adverse pressure gradient is such that the air is trying to flow forward from the trailing edge against the airflow, preventing the previously smooth streamline flow from following the surface of the aerofoil, and causing the low pressure area over the upper surface to collapse suddenly. Any pressure differential remaining is due to the pressure increase on the underside only. This condition is known as the stall, described fully in a later lesson. The whole surface of the aerofoil contributes to lift, but the point along the chord where the lift is effectively concentrated is termed the centre of pressure. The location of the centre of pressure, or CP, is a function of camber and lift coefficient, which depends partly on angle of attack. As the alpha increases from 0 to 16 degrees, the upper peak of low pressure, or suction, will move forward, taking the point of concentration of lift, the CP, with it. The magnitude of the lift force also increases with alpha, until the stall is reached, at which point the lift force decreases abruptly, and the CP moves back along the chord. Note that the CP is at its most forward point, where lift is at its maximum, just before the stall. A coefficient is a number without unit or dimension expressing a degree of magnitude. An aerodynamic force coefficient is a common denominator for all aircraft, regardless of weight, size or speed, and is a ratio between the average aerodynamic pressure and the airstream dynamic pressure. By this definition, a lift coefficient, or CL, is the ratio between lift divided by wing planform area, or lift pressure, and dynamic pressure. A drag coefficient, CD, is the ratio between drag divided by wing area and dynamic pressure. As speed increases, assuming a constant density, CD will remain constant, since drag pressure and dynamic pressure are increasing in the same proportion. We need to use coefficients of aerodynamic force, as they provide an index of the force, independent of area, air density or velocity, being derived from the relative pressure and velocity distribution. They are influenced only by the shape of the surface and angle of attack, since it is principally these factors that determine the pressure distribution. The last section of this lesson covers aerodynamic pitching moments. To refresh your memory, a moment is defined as the product of a force and the distance through which it acts. In the case in which we are considering the moment, it is purely a leverage, and no movement is involved. The distribution of pressure over a surface is the source of aerodynamic moments as well as forces. There are two ways of considering the effects of a changing angle of attack on the pitching moment of an aerofoil. Either by measuring the changes in magnitude of lift through a moving centre of pressure, or more simply, through a fixed aerodynamic centre. You know from the previous parts of this lesson that as the angle of attack increases, the CP moves forward and the magnitude of lift increases, and vice versa. This results in a changing force with a changing point of application. The aerodynamic centre, or AC, is a fixed point on the chord line, and can be defined as the point where all changes in the magnitude of lift effectively take place, and the point about which the pitching moment will remain constant at normal angles of attack. For subsonic airflows of less than Mach 0.4, the AC is located at the 25% chord point, regardless of camber, thickness or angle of attack. The AC is an aerodynamic reference point, which is used for examination of the theory of incompressible airflow, and is most directly applicable to longitudinal stability, as you will see later in the syllabus. There is a nose-down pitching moment about the AC, which is a product of the lift force at the CP and the arm between the CP and the AC. Since an increase in alpha will not only increase the lift force, but also shorten the lever arm as the CP moves forward towards the AC, the moment about the AC remains the same at any angle of attack within the normal flight range. With a symmetrical aerofoil at 0 alpha, the upper and lower forces are equal and symmetrically distributed. With an increasing angle of attack, the upper surface force increases and the lower force decreases. A change in the magnitude of the lift forces has taken place without a change in the position of the centre of pressure, which is a characteristic of symmetrical aerofoils. Thus, the pitching moment about the aerodynamic centre will be 0 at normal angles of attack, which is one of the big advantages of such aerofoils. To summarise the significant points of this lesson, we can start with the main things affecting airflow pattern, and consequently lift and drag. It will depend on angle of attack, airflow cross-sectional area change, aerofoil shape, that is, thickness and camber, again airflow cross-section, air density, air mass flow decreasing with greater altitude, and velocity, air mass flow, changing with TAS. The lift force is the result of the pressure differential between the upper and lower surfaces of an aerofoil. The greatest contribution comes from the top surface. Any contamination, particularly ice, or deformation of the upper leading edge surface can seriously disrupt the airflow acceleration, and hence the magnitude of the lift force. An increase in dynamic pressure with indicated airspeed will increase the lift force, and vice versa. An increase in angle of attack, alpha, will increase the lift force, and vice versa, over the normal flight range of 0 to 16 degrees. The centre of pressure of a cambered aerofoil moves forward as alpha increases, whereas the CP of a symmetrical aerofoil does not, within the normal range. Throughout the normal alpha range, the aerofoil's pitch-down moment about the aerodynamic centre, or AC, will remain constant. The AC is at the quarter-chord position for subsonic flow of less than Mach 0.4. The coefficient of lift is the ratio between lift per unit wing area and dynamic pressure. As alpha increases from -4 degrees, the leading edge stagnation point moves from the upper surface around the leading edge to the lower surface. The greatest positive pressure occurs at the leading edge stagnation point, where the relative flow velocity is 0. Form or pressure, drag, is the result of the pressure differential between the leading and trailing edges of the aerofoil. An increase in dynamic pressure, that is, indicated airspeed, will increase form drag, and vice versa. The coefficient of drag is the ratio between drag per unit wing area and dynamic pressure.